So we are still in section 10.1. This is part B, and we've looked at parametric equations of lines. We'll now look at parametric equations for circles and ellipses. We actually already know a lot about this just from our work with Trig. I'd like to consider the parametric equations, x equals cosine theta and y equals sine theta. And note that instead of t, I've actually used the parameter theta in this particular set of equations. Now, if we were to select values of theta and draw a graph in the xy plane, what would our result be? Well, if we draw the points xy equals cosine theta sine theta, what do we get? We just get the unit circle, right? Every point on the unit circle, we've known this since Trig, has coordinates cos theta sine theta. We're going to go ahead and try and generalize this a little bit by doing a couple of different things. First of all, we can go ahead and use the parameter t for time instead of theta. That doesn't hurt anything. It doesn't really matter what variable. And we can also generalize this to something that's not necessarily a unit circle, but can have a circle of any radius. Here's how we do it. Notice the x is still cosine, so instead of cos theta, I've got cos t, and the y is still sine, again instead of sine theta, sine t. Only this time, I've got this multiplier of a in front of that, cosine and sine. All that's going to do is it's going to make, for example, this 1 will turn into a 2 or a 3 or whatever a is, and it will give me that radius for my circle. So this is going to be a circle, still centered at the origin, with radius a. One comment, again, I think you're kind of used to this because of the way we think of our angles, but what direction do we move around this circle? If we were to just make a really quick little table of values here, and I'm going to just do the unit circle for now. When t is 0, x, which is cosine t, cosine of 0 is 1, and y, which is sine t, sine of 0 is 0. So that puts us here at 1, 0, at the starting point, t equals 0. If I then pick a new t value, and I'm just going to go to pi halves because it's easy to plug in. Cosine of pi halves is 1, and the sine of pi halves, the other way around. Cosine of pi halves is 0, and the sine of pi halves is 1. So here we are at t equal pi over 2, and you can see that we are moving in the counterclockwise direction around that unit circle. So it's a circle centered at the origin of radius a, traversed counterclockwise. Which from here on out I'll just abbreviate as CCW for counterclockwise. All right, a few questions. How much time does it take to make one complete circular path using our equations as given? Well, I think you probably know what it takes to go around a circle, but let's just continue the table just as sort of a verification. If I went to pi, cosine of pi is -1. Sine of pi is 0. So here I am at t equal pi. If I go to 3 pi over 2, x, the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is -1. So there I am at t equals 3 pi over 2. And then when I get to 2 pi, cosine of 2 pi is 1, sine of 2 pi is 0. So I'm back here again. Right, this all jives exactly with everything we learned in trig. We're just interpreting it a little bit differently now. We're thinking of it as the length of time it takes to go around the circle rather than thinking of the angles themselves. Right? So yes, it does take 2 pi seconds, or whatever our time units are. I'm always just going to use seconds, but it could be any units of time. 2 pi seconds to go around once. All right, we're now going to go ahead and try and change our equations a little bit to accomplish some different things. Next thing we want is we want a complete circle of radius 5, and we want it to take pi seconds. So this tells me two things. Radius 5, that's pretty easy to accomplish. We're just going to let the a value, the radius, be 5. But let's think about that pi seconds for a moment. Remember, under the original situation, it took 2 pi seconds. It now only takes pi seconds, so we're going twice as fast, right? And what do we do to go twice as fast? Same as before. We replace our t by 2t. So I'm going to go to my generic equations here, and I'm going to do both of those things. I'm going to say x equals, a is now 5, and I replace the t with 2t. And same for y, a is now 5, and I replace the t with 2t. So in order to kind of illustrate this, I've set up a little animation for us on Desmos that I'd like to take a look at. Let's see, it should be right here. So I started by just graphing a circle of radius 5, x squared plus y squared equals 25, and in fact I think I'm going to change that just to black. There it is. There's our circle of radius 5. Okay. In red, we're going to be seeing 5 cosine, just plain t, or I put in 1t for emphasis, 5 sine t. I've put these in as x values and y values. That's the equivalent of the parametric equation. X equals 5 cos t, y equals 5 sine t. Then in blue, we're going to consider the new one that we've come up with. X is 5 cos 2t, and y is 5 sine 2t. Watch the difference between the red point and the blue point when I start this animation, letting the t values run from 0 to 2 pi to go all the way around the circle. Do you see how the blue one's going faster? Twice as fast. Watch it. There's 2 trips for blue for every 1 trip the red point makes around the circle. So you can really see here how by doubling the t, replacing t with 2t, we've created an object that moves twice as fast around that circular path. All right, let's keep going. So next, we want to change our equations so that one complete circle of radius 2 takes 1 second. So radius 2 gives us an a value of 2 this time. In 1 second, well, let's see, it used to take 2 pi seconds, right? Originally, it took 2 pi seconds to go around once. So if we wanted to do it in just 1 second, that would be 2 pi times as fast. So we're going to have to replace our t with 2 pi t. Okay. So what's our new equation going to look like? X equals, a is 2, cosine of I'm replacing t with 2 pi t. And y would be 2 sine. Again, 2 pi t. Right? That gets me around this circle in exactly 1 second. And that one's really worth remembering, because a lot of times when I want to change the amount of time it takes, it's easiest for me first to adjust to 1 second and then to make a second adjustment from there. Case in point, this last part. Let's change our equations. So one complete circle of radius 10, so A is 10, takes 7 seconds. Here's how I'm going to handle the 7 seconds. I'm going to first of all say, well, I know that if I replace t with 2 pi t, that gives me 1 second to go all the way around. If I now want it to take 7 seconds, I really want it to go 1/7 as fast. So I'm going to replace t with 2 pi t divided by 7. Okay, that takes me from 1 second to 7 seconds. It's going slower, specifically 1/7 as fast as before. So what are our equations going to look like? X equals 10 times the cosine of 2 pi t over 7, and y is 10 times the sine of 2 pi t over 7. Now I will mention, you've seen stuff like this before. In trigonometry, we call this the period of the function, and it's the same concept, right? Just kind of a reminder here from Trig. We always knew that the period of the function was 2 pi divided by what we were calling the b value. And this was our b value. So here it would have been 2 pi divided by 2, or pi seconds is the period. Right? We could have done that for any of these. Down here, the period would have been 2 pi divided by our b value, which was 2 pi, giving us that 1 second. And this last one, here's my b value. So if I take 2 pi divided by 2 pi sevenths, the b value, and I invert and multiply, notice that I again get 7 seconds, just like we expected. So 100%, these are related concepts. We're just looking at it from a slightly different perspective now. Again, thinking of it in terms of the speed that we travel around the curve, rather than the period of a repetitive graph. But same exact concept. All right, let's continue to play a little bit with these circles. We saw that with lines, one of the things that we're able to do is change the direction. So we're going to play around a little bit with direction of motion for the circle as well. We already saw that when I had the equations x equals a cosine t and y equals a sine t, we were traveling in the counterclockwise direction. Specifically, our starting point was here on the x-axis, and then we traveled around counterclockwise. So we started at A0 and traverse counterclockwise. I would now like to write parametric equations that reverse that direction of motion. We'll still assume that we want to go all the way around once in a time period of 2 pi. We won't change that, but we just want to reverse the direction. So instead of traveling counterclockwise, we would now like to travel clockwise. There are actually 2 good ways to do this, And they're both valuable at different times, so I want to go ahead and talk about both. Option number 1, to reverse the direction of motion. Remember with the lines, basically we just thought about the slope instead of a positive number over a positive number. We thought of it as negative over negative. So ultimately, we just replaced t by negative t. That's one way to reverse the motion. And in this particular case, x would be a cosine minus t, and y would be a sine minus t. And I'm just going to use a couple of, hopefully at least in the back of your mind, familiar trig identities here. Cosine of minus t is actually equal to cosine of t. It's one of those negative angle identities. So we're still going to have a cosine t, but sine of minus t is minus the sine of t. So y is going to become minus a sine t. So that's one way to reverse the direction of motion. When you do this, let's just look at what happens at t equals 0. If I plugged in t equals 0, x would be a cosine 0. Since cosine 0 is 1, that's a. Now sine of 0 is 0, so the y value is going to be 0. So what happens here is we have the same circle with the same starting point, a0. But this time, we're going to go around clockwise. There's a second way of getting clockwise motion. This one's not as easy to figure out just based on the parameters, so I'm just going to tell it to you and we're going to kind of verify. What if this time I let x equal a sine t and I let y be a cosine t? So I've literally reversed the definitions of the x's and y's. This time, at t equals 0, notice again, sine of 0 is 0, cosine of 0 is 1, so my y value is going to be a. So this time I start up here at the point 0a before I go around clockwise. So two ways to get clockwise motion, depending on where you want your starting point to be. If you want to start on the x-axis, I would suggest using this method. If you want to start on the y-axis, I would suggest using that one. They both work. They just have different starting points. All right, so keeping that in mind, we're going to write some parametric equations for circles where we're going around clockwise. First of all, we have a circle of radius 4, so right away we know a equals 4. We want to go one clockwise circle every 2 pi seconds, and we'd like to start at 4, 0. So there's where we want to start. Given that we want to start at 4, 0 on the x-axis, option 1 is our better choice, right? That's the one where we started on the x-axis. So I'm going to go ahead and say x would be 4 cosine t, and then y would be negative 4 sine t. And that's all there is to it. All right, compare that to the next one. We want a circle of radius 1, so this time a is 1. We want to go clockwise again. We want to go once clockwise every 2 seconds. And we want to start at 0, 2. So let's see, I am going to have to change the period this time. I'm going to have to be careful with that. And then also, starting at 0, 2, I want to start up here. So this time, since I want to start on the y-axis, the second option is my better choice. I'm going to base everything on this. I already know that a is 1, so let me start with that. 1 sine, and I'm going to leave this for now, and y would be 1 cosine. That gets me the radius, and it also gets me the correct starting point. Now, as far as getting the 1 clockwise circle every 2 seconds, remember that to go to 1 second, t was replaced by 2 pi t. To get 2 seconds, I only want to go half as fast. So it would be 2 pi t divided by 2, or just pi t. So I'm going to say 1 sine pi t and 1 cosine pi t. Again, if you want to double check your reasoning, if you take the standard period of sine and cosine, which is 2 pi, divide by that number, pi, you should get the period, which we wanted to be 2 seconds. So we're good there. All right, one more of these. This time we want a circle of radius 8, traveling 1 clockwise circle every 6 pi seconds, starting at 0, negative 8. So 0, negative 8. We're starting on the y-axis again. We are starting on the negative y-axis rather than the positive. But since it's the y-axis, I think we're best off using this. So I'm going to start with x equals sine and y equals cosine. That allows me to start on the y-axis. Now in this case, I do know that the radius is 8. So I know that a is 8. So I have a multiplier of 8 here. But because it's exactly upside down compared to the previous one, I'm going to have to put negatives on the 8. Okay? That's what just tips it upside down. All right, what about the period? Well, let's see. 1 circle every 6 pi seconds. Usually it takes 2 pi seconds to go all the way around. So this is 1/3 as fast. It goes 3 times slower, or 1/3 as fast. So t gets replaced by 1/3 t. So I have negative 8 sine 1/3 t and negative 8 cosine 1/3 t. All right, so there are some examples of how to manipulate the circles to make the radius different, as well as how to change the direction of travel and the speed of travel. What about this next equation? What do you think the graph of these parametric equations would look like? Very similar to what we've been working with, but notice that there's a different multiplier on the cosine and the sine. What happens here is we're going to get an ellipse. Since x is the cosine term, this is going to go from minus a to a on the x-axis. And since y is the sine term, we're going to go from minus b to b on the y-axis. Because I have cosine for x and sine for y, this is going to go around counterclockwise. We could change the direction just like we did for circles. We could change the direction for ellipses. What if we modify it even a bit more? I still have my a cosine t for x and my y sine t, or my b sine t rather, for y. But this time I've added constants, x naught and y naught. That's going to move x every single point on your graph over by x naught and up by y naught. So this literally shifts the graph. Horizontally by x naught and vertically by y naught. Usually the easiest way to think of that is to think of that as then the new center point. The center point is going to go from 0, 0. So our new center becomes the shifted point, x naught, y naught, and everything else just kind of falls in place around it. Let's take a look at a couple of ellipses. This time I'm going to reverse things. Instead of giving you the equation and asking us to figure out what the graph would look like, I'm going to go ahead and give us the graph and say, hey, could you figure out an equation? I am not going to change the speed on these. I'm going to leave the period as 2 pi, but again, changing the speed would be the same as before. All right, so let's see here. We're going to have x equals, and on the x-axis, notice that we go from -2 to +2. So I'll have 2 cosine t. Y equals, here I'm going to go from -4 to +4. So that'll be 4 sine t. It hasn't been shifted. The center is still at 0, 0. And I guess I made the assumption, since nothing was shown to us, that this is going to be going counterclockwise. And there we go. All right, the next one. This one has definitely been shifted. The center is no longer at 0, 0. In fact, it looks like our center right here is at what? -2, 1? So that defines the x naught and the y naught for the shift in this graph. That said, notice that counting from the center, the x values go +3 and -3 from the center. So I'm going to start with x is equal to 3 cosine t. Again, counting from the center, the y values go up 1 and down 1. So y is going to be just 1 sine t. Then, to get the center to shift, I have to shift -2 in the horizontal direction, so -2 on the x, and I have to shift up 1 in the y direction, so +1 in the y. And once again, I made the assumption that we were going around counterclockwise. Had we wanted to go clockwise, I could, of course, have just reversed the x and the y. That would have worked fine. All right. A couple more examples for circles and ellipses. Oh, you know what, actually, before we do that, there was something else I wanted to show you here. I already kind of showed you that Desmos graphs parametric equations, your calculator does it as well. So if you don't happen to have access to Desmos, you can check your answers here by doing a parametric graph on a calculator. Here's how it works. If you go into mode, usually we're in function mode, but I'm going to change that over and make it PAR for parametric mode. And now when I've hit my y equal, it's actually going to ask me for different forms. It's going to have parametric forms. Let me get this old stuff out of here. There. Notice how for each graph it asks me for an x of t and a y of t. That's exactly what I want for parametric equations. So I'll tell you what, let's check our second answer. That one was the more complicated of the two. Let's type in 3 cosine t minus 2, and then just 1 sine t plus 1. Notice when I type, I'm just using the same key I always use to get x. It says x, t, theta, n. When I'm in parametric mode, it automatically gives me the t. I'm going to set up my window. And my t's right now are set up just the way I want. I want to go from 0 to 2 pi to go all the way around this ellipse. And I think that step was kind of generically generated by the calculator. It looks fine to me. All right. Just like the graph I see in my paper, I'm going to go like -6 to 6 for the x and y axes. So it looks pretty close to what I'm seeing on the paper. And graph. And there we go. You can see that ellipse just touching the x-axis like we expected, and it certainly looks like a reasonable choice based on the picture we were given. So again, in your mode on your calculator, so in the mode right here, you want to change to that parametric mode, and that's what allows you to graph these parametric equations. All right, in example 7, I've given us standard form equations for circles and ellipses, and I would like us to figure out how to write them in the parametric form, and we'll continue to assume counterclockwise direction for now. This first one, since the x squared and y squared terms have different multipliers, I already know it's going to be an ellipse. And what I like to do is I like to get it equal to 1. So I'm going to divide both sides of this equation by 36. That would give me x squared over 9 plus y squared over 4 equals 1. The x-intercepts, I would have, if y is 0, x squared over 9 equals 1. X squared is 9. X is plus or minus 3. And for the y-intercepts, if x is 0, I'd have y squared over 4 equals 1. Y squared equals 4. So y is going to be plus or minus 2. So based on that, my ellipse is going to look something like this, right? And we are going to go around counterclockwise. All right, so x would be, x goes plus and minus 3, so 3 cosine t. And the y's go plus and minus 2 from the center, so y would be 2 sine t. And we're good to go. Part B. This one's going to be a circle because notice the multiplier on the x term is 1 and the multiplier on the y term is also 1. So this guy's going to be a circle. This would be r squared for my circle. R squared is 16. So my radius is going to be 4. And then I'm looking here at the shifts. This has been shifted to the right 4. and then also down 1. Remember that when they're within the equation, you always have to take the opposite signs. So that means that my new center is at 4, -1. All right, let's write our parametric equations. X equals, radius is 4, so 4 cosine t, and y would be 4 sine t. And then to get the correct shift, I'd have to do a +4 on the x and a -1 on the y. One last example here. Find parametric equations for a circle of radius 5 inches, centered at the origin, so that the full circle is traced out in a clockwise direction every 60 minutes. Assume the units of time in your equation are minutes. And I'm sure you're all thinking, gosh, sounds a whole lot like a clock, and that's exactly what we're trying to model here. This is sort of like a clock where our minute hand has a length of 5 inches. All right, so let's see here. My radius is 5, and you know what? We should probably think about this for a minute. If we truly are modeling a clock, we already knew we wanted our radius to be 5 and our circle to be centered at the origin. And we were told that we want to go around clockwise, which would make sense again if we're modeling a clock. We weren't told, but if we really are modeling a clock, maybe it would make sense to go ahead and start up here on the y-axis, kind of imagining like your minute hand starting on the hour. So let's do that. This is sort of a choice, but I'm going to choose to start here. If you think back or look back in your notes, when we want to go clockwise but start on the y-axis, this is the one where we just reverse the x and the y. So instead of x being the cosine, x is the sine. So I'd have 5 sine, and y would be 5 cosine. All right, let's adjust for the speed or the period of motion. We know that we want our minute hand to go around once every 60 minutes. So what does that tell me? We already know that if we replace t with 2 pi t, that's going to give us 1 minute. Now I want to go 60 times slower than that. I want to take 60 minutes to go all the way around. So I would go 1/60th of that speed. Meaning t is going to have to be replaced by 2 pi t divided by 60. Or pi t over 30. So that's what I'm going to put in as my arguments for the sine and cosine function. And since we're centered at the origin, we don't have to add any shifts. We are simply done. So a little bit of modeling there with parametric equations of a circle. All right, that finishes up our parametric equations for circles and ellipses, so we'll stop there, and we'll come back and finish this section in the next video.